Good morning, everyone. Today we will be talking about induced magnetic force on wires that have current. We will also look at the torque and the potential energy for a loop that has a current going through and the existence of an external magnetic field. We will look at the magnetic dipole moment. In the coming lectures, we will continue with the Biot-Savart law. Okay, so we have seen how is the magnetic force is induced on a moving charge in the existence of a magnetic field. Now, we want to extend this further to look at the current going through a wire. In this case, if you recall, we looked at the Lorentz force, F equals to Q V cross B. That was for one single charge. Now in this wire, we have n number of charges inside this volume that is defined by this I, the length, and the cross section A. So the volume is AL. So the total number of charges inside this volume is NAL, and the total charge inside this volume would be NQAL. Now, if we look at those charges instead of one single charge Q, now we have NQAL. Then my expression for the Lorentz force would be now F equals to NQAL V cross B. And if you recall from a previous lecture, we defined that the current equals to NQA times the drift velocity. So now I can write this in terms of my current as F equals to where V, A, and Q is I. So I have I, L, where I here as a vector cross B, or I can now uh, swap the vector between the L and I. Instead of looking at I as a vector and L as a scalar, it could be the other way around, where F now can be equals to I L cross B. So this is the induced magnetic force on a wire that has a current going through. Now, what happens if here I have, this is for the uniform case. If I have a non-uniform case, then in this case, I have to use the integration. In this case, I will be looking at the dl as a differential element here. Now let's look at this question. And in this question, we have the following. A voltage source establishes a steady current in the closed wire loop shown. So in this case, this is the plus minus. So my current here is flowing in this direction. The loop is partially within a region of uniform magnetic field. So the magnetic field is uniform here. In what direction is the net magnetic force on the closed loop? So we have those sections. This is the section from here to here, and this section. They are within the magnetic field. The current is going in this direction. In this case, instead of looking at the velocity as we used to do for one single charge, now we will be taking the current, the direction of the current as my index finger here. So if I'm looking now at this part, the current is going up. The index, which is the direction of the index finger, the magnetic field is out of the page. right? Then the force on this side would be going this way. So this is, I'll call this one F1. Now let's look at this side. I have the current going downward. Magnetic field is out of the page. Then the force is in this direction. And this is again F2 here, where F1 and F2 are equal in magnitude. I have F1 equals to F2, so they cancel each other. So the only force that's going to determine what's going to happen to the loop is for the upper piece of wire. Here we have the index finger going to the left. I have the magnetic field pointing out of the page using the right hand rule. Then the magnetic force would be pointing upward. So this is F3. And in this case, the loop, the closed loop would be going up. So the answer to this is A. Now let's move to the next slide. Here, what is the magnetic force on the wire shown where W greater than L? So let's start with this side. This is side 1, 2, 3, and 4. So for side 1, I have the current going up. So the index finger is going up. I have the magnetic field into the page. Then F1 is pointing this way. For F2, index finger going to the left. The magnetic field is pointing into the page. Then F2 is downward. Si- Side number 3, index finger going downward. Magnetic field is into the page. I have F3 going this way. And for side number 4, index finger going to the right, magnetic field is pointing into the page, then the force would be upward. So this is F4. So here I have F2 magnitude equals to F4. I have F1 equals to F3. And in this case, the net force applied on this loop is 0. Example, we have a wire lies along the z-axis and carries a current of 9 ampere in the z direction. The magnetic field is uniform and has components Bx, By, and Bz. Find the components of the magnetic force on the wire. So here, if this is my coordinate, or this is y, this is x, and this is z. Okay, so here we have wire of 25 centimeters along the Z. So this is the 3D. Maybe you can have this one in a different color. Where L is 25 centimeters and carries a current 9 ampere in the positive Z direction. So the direction of the current is up 9 ampere. The magnetic field is uniform and has components. So we have B equals to minus 0.242 I minus 0.985, J minus 0.336, K. We need to find the components of the magnetic force on the wire. So A, find the component. So we have here I as 9 ampere. So L here is 0.25, K hat, and I is 9 ampere. So we have F equals to 9.25 K hat cross minus 0.242 I minus 0.985 J minus 0.336 K hat. So in this case, we're going to look at F equals to 9. Then we have here I, J, K, for 0.2500 minus 0.242 minus 0.985 and then minus 0.36. So this equals to 9. So we have for the I 0 times minus 0.3360 minus, which is plus 0 minus, we have here minus 0.985 times 0.25 I, then we have for J 0.25 times minus 0.242 minus 0 plus and K. K is 0. this equal to 9.246i minus 0.061j, and here f equals to 2.22i minus 0.54j newton. B, what is the magnitude? The magnitude F equals to square root of 2.22 squared plus 0.54 squared, and F equals to 2.29 newton. This is the magnitude of the force. Okay, so I'll let you try this on your own, and then we can discuss the solution in our live session. Now let's move to this example here where we have a loop, and this loop has a current I, and as given in this direction, and the magnetic field is in the same plane of the loop. So in this case, since we have the magnetic field being parallel and anti-parallel to those sides of the loop, then definitely the forces exerted on them would be zero. Why? Because the angle between them in this case is zero. I L cross B. So the angle between the the side here and the magnetic field is zero, and that's why sine theta would be zero, and this is going to result into a magnetic force of zero for the anti-parallel and the parallel cases. Now for the top and for the bottom, the forces are not zero. The angle is 90 degrees. So if we look at the top side, then taking the current as the index finger and the magnetic field going up, then I can see that the force is into the page. The same thing now if I look at the bottom side, the current going to the right, index finger is going to the right, and the middle finger will go up, then I have the force is out of the page. So in this case, although if you look at force, the net force applied on this loop would be zero. However, because those forces are applied, as you can see, on different sides, this is going to result into a torque. And in this case, this loop is going to rotate due to that torque, such that this rotation, looking at the applied forces on those sides, this one is entering into the page, this one is out of the page. So the loop will rotate such that it will be oriented perpendicular on the magnetic field. Now, if I am to look from this side, so imagine I'm looking now, I'm looking from here, I'm looking at that side. What am I gonna see? If this is my coordinates for this structure, and if I look at this side, I will see the x-axis this way. So this is now going to be the loop that I am seeing, I'm only seeing this side here. I'm only seeing this side, which is this one. And those are the forces that we have talked about. This one is this force that is entering into the page is going to look like this. And this force is this one that is out of the page. So in this case, this loop, it will rotate this way such that it will be oriented like this. Why? Because it will, as we will see later on, it will reach, this is its minimum potential energy position, so it will stay at that position. So how much is that torque? This torque, tau, is the force F times W over 2. So this is W over 2 plus F times W over 2 as well for this side. So the total would be FW. So that's the total torque applied on this loop, which is the length, the length of this side times the magnitude of the force applied on this loop. And in this case, it is, as you can see, it is perpendicular. This is the maximum torque when the force is perpendicular on that length. So let's move on. So we have found that the torque tau equals to the force times this length. And what is this force? This force is ILB. At that point, ILB. However, if I am to include for every position, then I have to include the sine theta between this W, this length, and this force. So here, if I rearranged, I can see now that this ILW is indeed the current times the the area, which basically here, this is the vector. And now here I have also the magnetic field as a vector, and the sine theta is the angle between this A and this B. So where is this sine theta? Now I can define a vector that is called the magnetic dipole moment. This magnetic dipole moment, that is mu, equals to IAN. Now this IAN, where n is the unit vector that is perpendicular on that loop. So here my theta is the angle between the n and the magnetic field. So again, this A is A n hat. Now for the coil, this loop, if it's made of several turns, where n is the number of those turns, then in this case, I can say that the magnetic dipole moment mu equals to Ni A n hat, where n hat is the normal unit vector that is pointing in this direction perpendicular on the loop. What does this mean? This means that if I am now to write the tau, the torque would be the magnetic dipole moment mu cross the magnetic field. This does not, the cross here does not define the direction of the tau. It only implies that the magnitude here of the torque is indeed mu b sine theta, where theta is the angle between the magnetic dipole moment and the magnetic field. Right now, at this location, I have an angle of 90 degrees, and here I have a maximum torque. The torque is maximum because sine theta now is going to be 1. So when the loop is parallel to the magnetic field, I have the torque being maximum. Now let's look at this loop and the magnetic dipole moment. How do we define the direction of the magnetic dipole moment? We are going to use the right hand rule, but this time we're going to use it this way such that the fingers defines the direction of the current that is curling in that loop. And the thumb will be the direction of the magnetic dipole moment. So in this case, the magnetic dipole moment based on the current rotating this way, then the magnetic dipole moment would be pointing up as we see here. So if we look at the magnetic bar here, we can see that there is a magnetic dipole moment for that bar that is equivalent to this magnetic dipole that we have introduced coming from this little loop. So this little loop is creating a magnet, a dipole, a magnetic dipole, such that it is equivalent to this magnetic bar. So this little loop is creating a magnetic field that is equivalent to the magnetic bar, and the magnetic dipole moment for this little loop is also pointing such that this is the north side and this is the south side of my dipole. Now, if you want to compare the magnetic dipole moment for different structures, we have, for example, the magnetic bar in the range of 1. We have the Earth in the range of 10 to the power 22. Now, let's look at this question here. Here we have a loop. We're only seeing half of it, just so we can have an idea about the direction of the current. So in this case, the half that is inside the page does exist. The half that is outside has been removed. But here the question is asking to rank the magnitudes of the torque acting on the loops from the highest to the lowest. All loops are identical and carry the same current. We can define the magnetic dipole moment using the right hand rule. So here for case A, I have the current entering into the page and then coming out of the page, which means based on the right hand rule, I have the magnetic dipole moment pointing in this direction. For case B, I have the current entering from here, leaving from here, which means based on the right hand rule, I have the magnetic dipole moment that is perpendicular on the loop pointing in this direction. However, here I have the magnetic dipole moment pointing up this way. And if you remember, we said that we have a maximum torque when we have the loop parallel to the magnetic field. And in all cases, we have a maximum torque when the loop is parallel to the magnetic field, which is this case. Why? Because here, if you look at the angle between the magnetic dipole moment and the magnetic field, the angle is 90 degrees here, where I have sine 90 degrees equals to 1. Here it's less than 90 degrees, which basically means that the torque applied here is less than case C, so case B is less than case C. And here we have the angle between the magnetic dipole moment and the magnetic field equal to 0, and that's why the torque here is 0, and C is the maximum, and B is in between, so we have the answer being B. So C, then B, then A. So the torque equals to the magnetic dipole moment across the magnetic field. And we have seen that the torque would be zero based on the sign. So this equals to mu b sine theta. And we have seen where is this theta between the magnetic dipole moment and the magnetic field. We have two cases where where theta is zero. We have a stable one where the magnetic dipole moment is in the same direction as the magnetic field, parallel. This is a stable position. And we have another position where the magnetic dipole moment is anti-parallel. And in this case, this position is an unstable position, although the angle here is 180 degrees and sine 180 degrees is zero, but this position is an unstable position, and any vibration, any perturbation will result into the loop flipping and coming into the parallel case. So this one is the unstable position, and this one is the stable position. So in all cases, the loop will rotate such that the magnetic dipole moment will align with the external magnetic field. So let's look now at the potential energy. This position where we have the angle between the magnetic field and the magnetic dipole moment being 180 degrees or the anti-parallel. This position is the position where you have the maximum potential energy, where here when they are parallel, the magnetic field parallel with the magnetic dipole moment, then in this case we have the lowest potential energy in this case. And this is given by this expression. For this question, we have the following. We have a coil. A circular coil lies in the xy plane with the area A, n turns, and current I. The coil is free to rotate about the diameter along the x-axis. So this is my axis of rotation. The magnetic field is pointing in the y direction. What is the initial magnetic dipole moment vector for this before responding to the magnetic field? So we need to find the initial location, the direction, and the magnitude for the magnetic dipole moment before responding to the magnetic field. So we know the magnetic dipole moment mu equals to n I a n hat. So the magnitude is NIA. And the direction based on the right hand rule, if we look at the current using the right hand rule, where the current is the fingers, the rotation of the current is defining the direction of the fingers, and then we will see that the thumb will be pointing in the z axis. So this is going to be the direction of the magnetic dipole moment before responding to the field. So the answer to this would be along the z-axis. Now, what's going to happen? How is it going to respond here? It will respond such that it will rotate to align with the magnetic field. So let's look now at the second question here. There's a circular coil lies in the xy plane. Again, same question here, and the coil is free to rotate along this axis here, the x-axis. The magnetic field is pointing upward. What is the torque exerted on this coil? So the torque, we know that the torque tau equals to the magnetic dipole moment across the magnetic field. And we know from the previous question that the magnetic dipole moment is along the z-axis. So in this case, the angle between the magnetic dipole moment and the magnetic field is 90 degrees, and we said that the coil will usually rotate such that the magnetic dipole moment will be aligned with the magnetic field. So this is position one, this is position two, this is where the magnetic dipole moment is going to be. So it will rotate about the x-axis such that the magnetic dipole moment will be pointing in the y direction. So now the torque is going to be NIAB and this location, and sine 90 degrees is 1. So here, because sine 90 degrees is 1, so it is NIAB, and it will rotate about the x axis. So the answer is C. Uh, in this question, we have a circular coil lies in the XZ plane that has an area A number and N number of the turns and the current I, and the current is going clockwise this way. The coil is free to rotate about a diameter along the x-axis again. So this is the axis of rotation. The field B is in the y direction. Again, the field B is into the page. What is the torque exerted on this coil? So in this case, since the current are going clockwise using the right hand rule, for the clockwise, I can see that the magnetic dipole moment would be pointing along the y-axis. So this is going to be the magnetic dipole moment, which is basically already aligned with the magnetic field. The magnetic field is also pointing in the y-axis. So in this case, the torque is mu cross B. However, the sign here, theta is 0, which means the torque now would be 0, and the answer to this would be A equals to 0.